In this experiment, I investigated motion observations of a star in space and used Newton's second law to analyze the influences from the surroundings acting on the star, which I found to be the gravitational force equal to 4.09 times 10 to the 23rd newtons, as well as using Newton's law of universal gravitation to identify the mass of the black hole around which the star orbits, which I found to be about 12 times the mass of the Sun. Using what we can observe of the system, the star, we can find the total net force acting on the object. Here, we see that we can use the mass of the star as well as the calculated velocities from the position data and divide that by the amount of time taken in or observed in this experiment to find the momentum acting on the object. This momentum can be divided into two components: the parallel component, which is the component that causes the object to speed up or slow down, as well as the perpendicular component, which is the component that causes the object to turn. These components form the momentum vector here, which is about equal to the change in the momentum over the change in time, which we can equal to F net by Newton's second law. To complete the experiment, I can use the given star mass here, as well as the F net we found before, to find the mass of the black hole by using Newton's law of universal gravitation and the star from the black hole distance represented here. To model the star's motion, I entered in the given information the star's mass, as well as delta t representing 1 day in seconds, and also read in the position data from the CSV file given to us on WebAssign. Here in this loop, that position data is extracted to be assigned to separate values in order to find the velocities. The net force was calculated by changing the code in this loop here. You can see that here and also here, the values of F net perpendicular and F net parallel have been assigned. These values are different from dp dt parallel and dp dt perpendicular in that they are the parallel and perpendicular components of the F net vector specifically, and also add together to equal the total net force. This net force is also different from the change in momentum over change in time, which represents the net force but is not the same. Next, I used the F net found here to calculate the mass of the black hole, which I specified here. Then I created arrows to display the F net, F perpendicular, and F parallel vectors with the star's motion, and corrected the size to help the arrows to fit the star object and not necessarily the magnitude of these values. Lastly, I had the program print the F net as well as the star position and the black hole mass. Here you can see the star's predicted trajectory as well as the parallel component of the net force, the perpendicular component of the net force, and the net force itself pointing towards the black hole to represent the gravitational force. This parallel component also represents the force parallel to the object's velocity, which is in this direction. The code, as expected, outputs the total magnitude of the net force here, as well as the black hole mass, which is here, 2.414 times 10 to the 31st kilograms, which I calculated from the mass of the Sun to be 12 times that mass. You may wonder, what if a new black hole were to replace the current one, but the star's motion would still only be affected by the gravitational force? What would happen then? Could the black hole be of a different mass? Well, the answer to that question is yes, because if the star's motion changes, orbit changes, or speed changes, then we can use the same process from the process we used before with the old black hole to inevitably find a new F-net here, which means a new gravitational force, and with Newton's universal law of gravitation, find a smaller or larger mass of the black hole.